Hey folks, welcome to Chapter 3 in our pre-calculus class. This entire chapter, including this lesson, is going to count for the second marking period. So, it's going to be graphing sinusoidals. We're going to be spending 2 days on this lesson, so today it's going to be graphing sinusoidals from an equation by hand, and then tomorrow it's going to be more in-depth stuff. Anyway, let's begin.
So we're first going to start off with these rather confusing looking equations. I promise their bark is much worse than their bite. They're the same equation, one just has cosine and one just has sine. So you don't have to worry about each one being different. For our purposes today, they're basically the exact same thing. One just has sine, one has cosine. Now let's talk about A. A is the amplitude. It's how much taller or shorter we make the graph, and you've seen it before as the vertical dilation. It can be positive or negative. We're going to focus today on just, actually both. Now, B is going to be our reciprocal of the horizontal dilation. If you're wondering why B is the reciprocal instead of just the horizontal dilation, it has to do with the fact that B is inside the trig function. And just like we know from our transformation on functions, whatever is inside the parent function is flipped. So because B is inside sine, it's inside cosine, the value of B is the reciprocal of the horizontal dilation. So if B was 5, that means the horizontal dilation is 1 over 5. If B was a fraction, you would flip it to find the horizontal dilation. Now C, this one looks complicated because it's sinusoidal axis, and you might be thinking, oh my goodness, we have another axis. All that is the vertical translation, how much you move it up or down. And then D is the phase displacement. You might be saying, oh my goodness, what the heck is the phase displacement? It's just the horizontal translation, how much we move it left or right. Now notice that B and D are inside, so they're always going to be the opposite sign of what you expect. And then A and C are outside, so they're going to be the same sign that you would expect. Now, the period of a function, how long it takes to complete a full cycle, can be calculated from the value of B. Now, since 1 over B is the horizontal dilation, like we discussed on the previous page, and since sine and cosine, the parent functions, have periods of 360, the period is found by this. Which looks really confusing until you realize, wait a second, this is just my horizontal dilation. And then this is just the frequency of the parent function, so the original. Which is exactly what we've done before in the past by just saying, well, we have our dilation, and I'm applying it to the original. Now, the reciprocal of the period, which is the number of cycles per degree, is called the frequency. Now, you can find the frequency given the period, you can find the period given the frequency, and here's how. For instance, we just went over this portion of it. The period is equal to the reciprocal of B times the original. And then the frequency is just 1 over the period. So the frequency here is just the original one flipped on its head. And that just happens to equal the coefficient of B over 360. If you're wondering how that happened, well, we just flipped this. And then we flip this, and we just combine some fractions together. Which means that given the frequency, you can find the period. Given the period, you can find the frequency. Now, we're going to graph today by transforming the original functions, and we're going to be focusing on critical points. The critical points are the things that we already know about sine and cosine. They're the high points and they're the low points. We know that sine has high points at some places, low points at others. We know that cosine has high and low at some points as well. Now we're also going to use the points of inflection, which is just where it crosses the midline, also called the sinusoidal axis. The reason why it's called the point of inflection, which would be right here, is because up here, the curve is downward, but over here, the curve is upward. And this point of inflection right here, point of inflection, is where it shifts from concave down to concave up. Here are the original ones. These are the original sine and cosine functions. I've graphed them out. Our critical points for sine, we have a critical point there, we have a critical point here. We have a point of inflection at 180, and you also have a point of inflection at 0, and a point of inflection at 360. So if I just told you some information about sine, for instance, where to find one of these 5 points, and how long the cycle is, you could find the rest. Now the parent function of cosine, very similar. The only difference is it starts at a maximum. So those are the critical points at 0 degrees, 180 degrees, and 360 degrees, and the point of inflection is at 90 and 270. And it would continue on and on and on and on and on forever. Let's take a look at how we would use this information to graph out a few things. So let's take a look at how we would go about doing this. We're given an equation, and we're going to pull this information out. We're going to pull out the dilations, the period, the amplitude, the displacement, the vertical displacement, and we're going to sketch our graph then. We're going to do all this by hand, and we're going to be using this cosine equation, which is given to us. So, our horizontal dilation factor. Remember, horizontal dilation factor is this. It's the reciprocal of whatever that is, because it's inside the cosine function. So that means that's going to be a half. Well, then the period is just a half times 360 degrees, so it's going to be 180 degrees. Be sure to include the degree units. You're going to see why that's very important coming up, but I'm going to be a real stickler for including degrees. Now, suppose then we're going to move on to the amplitude. Well, amplitude is going to be given by this, so the answer is just going to be 3. That we can just pull straight out of the equation. Next, let's talk about our phase displacement. Phase displacement is here. I'm including the sine in it, and that's going to be 70 degrees to the right, because remember, it's inside the cosine function, we're doing the opposite. And then, last but not least, we have the vertical displacement, which is out here. It's outside, so that's going to just be 4 degrees up. It's outside, so it's the same thing. Same direction we would expect. Positive means up. So now let's get a bit more room on this page. We're going to use this information, and we're going to sketch it out. Now, it's always a nice idea to start with our vertical displacement. So I'm going to start with the vertical displacement. It's 4 up, so 1, 2, 3, 4. And I'm just going to draw a dashed line. You can think about these lines like just guidelines about where we're going to draw these things out. Now, the amplitude. Amplitude is 3, so I'm going to go up 3 from my vertical displacement, 1, 2, 3, and draw similar lines. And I'm also going to go down 3. Alright, because that's going to be my max and my min. Now, I'm going to use my phase displacement now. 70 degrees to the right. Okay, so I'm just going to go over to here. Let's call this 70 degrees. And this is a cosine function. This 70 degrees is where the function starts, and it's cosine, so I know it starts at its maximum. So right up here. Okay, now I know that the period is 180 degrees. Because the period is 180 degrees, this is going to take 180 degrees to complete a full cycle, so I can start at my 70 degrees, I can add 180 to it, and 180 and plus 70 is going to be 250. And it's, again, a cosine function, so that means it's going to end on a high note as well, over here. You might say, well, wait a second. We have 2 points here. How do 2 points give me anything? I need a bunch. Well, we do. But halfway between these 2 maximums because this is a cosine function, there's a minimum down here. Then halfway between the 70 and this minimum, there's a point of inflection here. Then halfway between this minimum and the green maximum, there's another point of inflection here. Now remember, cosine curves, so you're not going to want to draw straight lines. You're not going to connect these and just go straight. You're going to curve the line. So let's do it in orange, because that's a new color. So it's going to start out and go something like that. And we've just graphed it out using the equation and without a graphing calculator. Now, let's check how we would do it and just check our work with the calculator on Desmos. We're going to plug in this equation into Desmos right over here, and we're going to see if we're good to go. Now, here's the important thing when you're plugging into Desmos. Before you even begin, go over here to the graph settings, go down to the bottom, click degrees. It's in radians to begin with. We're not graphing in radians yet. So, just going to plug it in. We got our graph. Now, let's check to see if we got it. I can go to my table, and I'm going to see if at 70 degrees I'm at a maximum, if at 250 degrees I'm at that same maximum. I can even check points in the middle. So, right in between 70 and 250. It's going to be 160, and it should be at my minimum there of 1. I am. You can also, if you want, change the settings over here and have the x-axis go from 0 to 250 to check it, and then have the y-axis go from 1 to 7. It looks just like what we had. So let's take a look at this one. Same deal. Difference is here we have sine instead of cosine. So that's going to slightly affect how we do these things, but not much. We're still going to start off by identifying what our horizontal dilation factor is. That's what's right next to sine here. And because it's inside the trig function, it's 1 over 30. And then the period is also given by that information. So that means it's 1 over 30 times 360 degrees. And you divide 360 by 30, and you're going to get 12. Now, the amplitude. Amplitude here is given by 4. So that's cool, and it's just like what we would expect. So the amplitude is 4. And then our phase displacement is given by this. Notice it's a positive inside, so that means it's negative out here. I'm going to say 1 unit to the left, because it's inside the trig function, is going the opposite direction. Then my vertical displacement is just given by this -2. It's outside, so it's the same deal, same sign, same direction we would expect, so it's a -2. Let's get a bit more room here to graph it out. So we're going to start with the same way that we did before. I'm going to start with my vertical displacement at -2. I'm going to extend it a little bit here too. You'll see why in a moment. Then I need my amplitude of 4. So I'm going to go 4 in either direction. 1, 2, 3, 4. And then 4 down. Cool. So I've used vertical displacement. I've used my amplitude. Now let's use the phase displacement. It's 1 unit to the left, so that means I'm going to have to move my graph 1 unit in this general direction. However, this is a sine function, as it says up here. So that means that it's starting at the midline. So I'm going to go over to here. This is at -1 degree. And we're good. So I've used my phase displacement. Now, we know the period is 12 degrees. So I'm going to add 12 to that -1, and I'm going to get 11. And that's using the period. Now, you might say, okay, fine. What do we do now? Well, you need to think about the parent function of sine. Remember, that parent function goes up, hits a critical point, goes down, hits an inflection point, goes down, hits a critical point, and then goes back again. Basically, it looks like this. Well, we have this one, we have this one, which means in the middle right here, there's a critical point. In between the critical point and the starting point, it goes up. In between the point of inflection and the end, it goes down. So that means that our graph looks like this. And we're done. The thing to keep in mind when you graph this on Desmos is this is a very, very, very squished graph, which means that it's going to repeat a lot in between 360 degrees. I mean, it's going to repeat 30 times in 360 degrees. That's a lot. It's going to look squished when you graph it out, but check to see if the points are the same. Now, let's take a look at doing all this from a graph. So once you know the connection between the equation of a sinusoid and its graph, you can go backwards and write the equation for a given graph, which is really nice and important. So for the following, we're going to write the period, the horizontal dilation factor, the amplitude, the phase displacement. For the cosine function, they were very specific as which one, which is important. We need to know that. And the vertical displacement for this particular equation. Cool. Now, let's start off with the period and work our way down. So the period, this is a cosine function, so it's going like this. And it's stopping right here, so this is a full cycle. Starts at 10, so it goes 10, 20, 30, 40, 50, 60. The period is 60 degrees. So the dilation factor, so it was 360 in the original function. Now it's 60 degrees, so I get this by just doing 60 over 360. That equals 1/6. You'll notice here that my degree symbols have canceled each other out. That's okay. Now, if the we'll get to that in a second, never mind that. So, my amplitude. Well, my amplitude here was given by how far away from the midline I am. And you can think about the midline by just finding the difference between the two. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, 1, 2, 3, 4, 5. This is our midline. It's halfway between the two of them. And then my amplitude is just what takes me up to here. Well, this is 5. So that's my amplitude. My phase displacement, so how far over I am. Well, I know that this is a cosine function, and cosine starts at the maximum. But here, the maximum is at 10 degrees. So my phase displacement is 10 degrees to the right. So vertical displacement. Well, normally it starts at 0. The midline, or the sinusoidal axis, is at -3. So this is going to be 3 down. So now we have all of our information. We're going to use this to make our graph. Our equation. So y equals, and let's start with our vertical displacement. So it's 3 down. Then it's going to be plus my amplitude of 5. Now it's a cosine function, so that's going to be cosine. My horizontal dilation factor is a 6, but it's inside, so I got to flip it, so it's a 6. And then my phase displacement is 10 to the right, which means that instead of positive 10, it's going to be negative 10 degrees. And that's my equation. You can check it in Desmos by plugging in. You should get something that looks like this.
Cool. So you've seen how to use critical points. You've seen how to use points of inflection. You've seen how to check on Desmos. Don't forget to change it to degree mode because those radians will sneak up on you. Now you're going to go and give those textbook questions a shot. All right? Give them a shot. Put them in the doc. You're good to go. Have a great day, folks. Talk at you soon.